All right, welcome to lesson 22. And today's lesson, we're going to talk about one more formulation. It's going to be the home improvement building supply company that you'll find on page 650 of your textbook. I'll read through this briefly. The home improvement building supply company has received the following orders for boards in 3 lengths. The company has 25-foot standard length boards in stock. Therefore, the boards must be cut into lengths necessary to meet the order requirements. Naturally, the company wishes to minimize the number of standard length boards used. The company must therefore determine how to cut up the 25-foot boards in order to meet the order requirements and minimize the number of board lengths used. So that's the essence of the problem. And this is one of my favorite problems because it shows the creativity of linear programming and how you can think differently about a problem in order to approach it, in order to solve it. And so it's quite a creative process. So the first thing, again, we're going to go through our process. What is the decision? What are the decision variables? What's the objective function? And then, what are our constraints that we have to satisfy? So, and it's a really, really good problem. I give you a hint there, but let's talk about this as we go forward. Okay. Here's again the problem restated in a slightly different way, but essentially there's the amount of boards that we need to meet. We have to have 7-foot, 9-foot, 10-foot boards, 700 of the 7-foot length, 1,200 of 9 feet, and 500 of 10 feet. So we have to first determine here what the decision is. Of course, decision is how we're going to cut the boards, but the question then becomes a little bit more complicated and precise. And if the help, if you're the shop foreman and you have employees who are on the line, what information do you need to give to those folks who are cutting the boards? And you have to envision yourself at one of these large lumber yards, and you've got stacks and stacks of these 25-foot boards. So in a sense, an unlimited number of those 25-foot boards. But how do you tell the shop foreman to cut them? So that's the essence of the issue, and how does the shop foreman tell the workers how to cut them? So I'm going to pause for a minute. This is one of the problems. If we were in class, we would spend a lot more thinking about this and talking through this. But let's talk about this for a minute. How are you going to? What information do you need to provide to your staff, to your employees, in order to meet the demand for this order? So let me pause for a minute. Let you think about that. Okay, hopefully you didn't rush through this. Feel like I should have had the Jeopardy theme song playing in the background, but let's move forward a little into this and start talking about it. So this diagram, of course, represents one of the 25-foot boards, and one of the ways you could cut that 25-foot board is you could have three 7-foot sections, and then of course you'd have 4 feet left over if you used the 3 7-foot sections. That 4 feet of leftover board is called trim loss. So, this is a whole nother issue with respect to the trim loss. So the issue becomes, of course, if you only cut these boards, you would only have 7-foot boards, and if you cut 100 of these, then you would have the excuse me, not 100. If you cut 30, 700. Anyway, if you cut, do the arithmetic, 3 into 700, that number of boards, 250 boards or 220 boards, you would meet your demand, but you wouldn't for 7-foot, but you wouldn't have any 12-foot boards. So the question becomes really, what patterns are available to cut these boards in, and how can we cut these boards? And so that's a problem that's fairly easy to solve. There's a finite number of possible patterns. And so let's move on to the next slide. This is a problem I wish that you would have a little more time to wrestle with, but let's move on to the next slide and see, well, lo and behold, there's only 6 feasible cutting patterns. And what I'd like for you to do is convince yourself that there's not another possible way to cut these boards. There's 4 ways actually to get 7-foot boards. You can use pattern A, B, C, or D to get a 7-foot board. For example, for pattern B, you can cut 2 7-foot boards, a 10-foot board, and have 1 foot of trim loss, and so forth, all the way out until F. You could cut 2 10-foot boards and have 5 feet of trim loss. Then you'll notice none of these trim loss pieces will satisfy any of the boards that you need. And there's one case where you cut 1 7-foot and 2 9-foot pieces where it uses exactly the whole board. And that would be good and efficient, except if you only used the pattern D, you'd never get any 10-foot boards. So then the problem becomes, what then still, if these are the feasible cutting patterns, what are the decision variables? And so I'd like for you to do 2 things. Number one, on your own, convince yourself that these are the only possible cutting patterns. There's only 6 choices. And so now we're still faced, and I'm going to just say with prejudice in some sense, that these are the only feasible cutting patterns, but we still haven't identified our decision variables. And again, what's a decision variable? It's a letter or a symbol that stands for a number. All right, and so I'm going to go to the next slide, and we're going to talk more about that, and we'll talk directly about our decision variables. So our symbols are the following: that we're going to let the letter A stand for the number of boards cut that use pattern A. And again, as you will have seen in all of our cases, we're starting off our definitions of the decision variable with the words the number. It's got to be, decision variable has to be a number that represents, in this case, the number of boards that are cut using pattern A. So I don't know what the solution is, but what you need to tell your employees that are actually doing the work is, well, you need to cut 400 boards using pattern A, 300 boards using pattern D, and 200 using pattern E, 100 using pattern F, and so forth, in order to meet your, maybe 0 using pattern B, in order to satisfy this order. Okay, so those are our decision variables. Then the next question is, what's the objective function? Well, clearly in this case, we want to minimize that objective. And in this case, we want to minimize the total boards used. So that's one way to express that. And then the question again then becomes, well, how do we calculate the total number of boards that we're going to use? And that's the next issue. This is, I think, this will blow your mind in some sense as well, because how are we going to calculate the total number of boards that are used? I want you to think about that for a minute. How we've done this before, but remember now the definition of our decision variables. A is the total number of boards. A is the number of boards cut using pattern A, B using pattern B, and so forth. And so if you think about it carefully, and I almost hate to give away this answer, but the total number of boards is going to be equal to A plus B plus C plus D plus E plus F. And that's our objective function. It's the total of the total number of boards used. And so A is the number of boards with pattern A, B pattern B, C pattern D, and so this sum represents the total number of boards used. Okay, so that's our objective function. So the objective function, again, we summarize. A plus B plus C plus D plus E plus F. Okay. So now let's go on and talk about our constraints. So, how are we going to address our constraints? And we really will know in each case. For example, we need to have at least we need to meet at least equal to or greater than 700 boards. We need to have equal to or greater than 1,200 boards. We need to have equal to or greater than 500 10-foot boards, and so forth. So that gives us a start. But the question is, if we use these patterns, how many 700-foot boards are going to be, how many 7-foot boards are going to be cut? So let's go back and look back at our pattern. So if we use pattern A, how many boards are going to be cut? 7-foot boards are going to be cut. Well, you'll see for pattern A, there's going to be 3 7-foot boards. And for pattern B, there's going to be 2 7-foot boards. And for pattern C, there's going to be 2 7-foot boards. For pattern D, there's going to be, one. And then for pattern E, there's going to be no. And for pattern F, there's going to be no 7-foot boards. So what we've created here is essentially that constraint, the left-hand side of that constraint for the 7-foot boards. And so the way we're going to go back, and the way this constraint will look for the 7-foot boards is 3 times 3A plus 2B plus 2C plus D is greater than or equal to 700. Now, you'll notice, I want to say something about this too. You'll notice, of course, we did not include E or F because the coefficient of E and F is 0, and so they don't need to be included in this equation. And also, you'll notice the coefficient of D is 1. And so we don't necessarily have to include that coefficient because it's understood there that 1 times D is in fact D. So that's our constraint for our 7-foot boards. And we're going to go back and we're going to construct the same situation for our 9-foot boards. And so let's go back to our slide and look at our 9-foot boards. We have no 9-foot boards on A, none on B. We have 1 on C. We have 2 on D. We have 1 on E, and we have 0 on F. So we only have 9-foot boards on patterns C and D. So then that constraint becomes, for our 9-foot boards, it's 2C plus D is greater than or equal to 1,200. So there's going to be a lot of those boards that are cut in order to meet those 9-foot board, 9-foot boards. And then lastly, we'll go back and look at our 10-foot boards, our 10-foot lengths, and there's 1 10-foot board on B. And then there's 1 10-foot board on E, and there's 2 10-foot boards cut on pattern F. So B, E, and F. And so if we go forward to our constraint, for the 10-foot boards, it's going to be B plus E plus 2F is going to be greater than or equal to 500. That's going to be our constraint, and in that way we'll satisfy, with all 3 of those constraints, we'll satisfy our orders. And then, of course, we don't always will remember non-negativity, which A is greater than or equal to 0, all the way up to F is greater than or equal to 0. And that completes our constraints. All right, so the next question is to show the complete formula altogether. And you'll notice here's the recapture of all those particular cutting patterns. We have all of our cutting patterns listed here. We have the trim loss for each one of them listed in the bottom section here. And we'll notice we're going to let the index I equal the number of boards cut using that pattern for A, B, C, D, E, or F. And then we're going to minimize the number of boards used. And then we have our 3 constraints where we have to meet each one of these. And again, you'll see, it's interesting, you'll notice that this left-hand side of this constraint matches exactly the coefficients for these respective patterns. The coefficients are 3, 2, 2, 1, 0, 0. And that's exactly what we have here. So that's the complete formulation. The last thing I'm going to leave you with and I want you to think about is the following. There's an alternate objective function. So suppose rather than minimizing the total number of boards used, suppose home improvement supply company wanted to have the minimum amount of feet of trim loss. So I'm going to leave this to you for an exercise. What would that objective function look like? Hopefully that you'll see that that's pretty straightforward after you've thought about the problem. The next lesson is going to be in lesson 22, we're going to go in and we're going to solve this problem in Excel. Okay, think about that. Make sure you understand the formulation. And then the next video, I'm going to show you how to solve this in Excel.